Okay, so we talked about conduction, we talked about convection, and now is the third and last way through which we can transfer heat, which is radiation. What is very nice about radiation is that different from convection and conduction, which need a medium. No? So for convection to happen, or conduction to happen, we need a medium, no? Because we have the collisions of molecules, we have this big um, flow of masses happening. In radiation, we don't need any medium. Yeah, and a typical example of that is the heat that we get from the sun. The sun is radiating, is sending energy through the vacuum that comes all the way to us. Okay, this amount of energy per time, this flow of energy that we get through radiation is given through this equation here. So let's see all the terms that we have in this equation. First, an important thing, it will depend on the temperature of the source, and it depends on this temperature to the power of 4. So this is very important, and I'm going to repeat this later, but we have to enter this temperature in Kelvin. Okay, so the case of the sun, for example, we would enter here as a temperature something close to 6,000 Kelvin. What else do we find in this equation? A here is the area of the source. In the case of a star, usually we think about the area of a sphere. We also have this constant, this sigma here, this Greek letter, the name of this Greek letter is sigma. This sigma is a constant and is given by this value here. This constant is called the Stefan-Boltzmann constant. And this E is what we call emissivity, which tells us what kind of surface we have. If we have a black object, an object that is good at absorbing, this object is also good as emitting radiation. So this E is going to be close to 1. On the other hand, when we have a shiny object, these objects, they are good at reflecting. They're not good at absorbing, and they are also not good at emitting. Okay, so this E here is the emissivity, which is just a number between 0 and 1, which characterizes the kind of surface that we have. Okay, so this equation here is the amount of heat that is going to be radiated by a certain source. But we may ask, what is the net flow? Because the source may be emitting, but it can also be absorbing radiation from its surrounding. So the net flow rate of radiation is whatever the object is emitting, which is this T1 here of the object, minus what it absorbs from its surroundings. So this T2 is the temperature of its surrounding. Everything emits radiation, not just the stars, not just the sun. Every object emits. Now, why is that? Pick a table, pick the walls, pick anything. Any object is made of molecules, and these molecules are vibrating. This vibration of these molecules depend on the temperature of this object. As we have these vibrations, the consequence of these vibrations is the emission of radiation. Okay, so everything is going to emit. The difference is that if this object is cold, it's going to be emitting, for example, in the infrared, so we cannot see that. But if it's a little hotter, it will be emitting in a frequency that we can see, which is light. But if it's very hot, it will be emitting at frequencies that are even higher, like the ultraviolet, which we cannot see. Okay, but any object is emitting. Okay, given that, we are going to now solve a problem, but let me first write down this equation because we are going to need it in the next slide. So the net flow, as we said, is delta Q divided by delta TT, here is time, depends on the emissivity, depends on this constant, the Stefan-Boltzmann constant, and let's write this constant here. The Stefan-Boltzmann constant is 5.67 10 to minus 8. Let's have a look at the units now. Watts, so joule per second, divided by meter square, divided by Kelvin to the fourth. So this is the important thing that I told you I was going to repeat. The units of this constant tells us what are the units of the other quantities that we have to enter. Since here we see Kelvin, well, we know that the temperature that we're going to enter has to be in Kelvin. Be very careful. This is a very silly mistake. If you enter this temperature in Celsius, you're not going to get the right answer. So you have to enter this in Kelvin. And the units of the constant is already telling us what is the unit that we should use for the temperature. Okay, what else do we have? The area of the surface. Okay, so I'll put this area here. Then we have T1, this is the temperature of the source to the fourth, and this temperature is in Kelvin, minus the temperature of the surrounding. This T2 is the temperature of the surrounding, um, um, also to the fourth. Okay, so the source is going to be emitting, and it also will be absorbing. So the net flow is what the source emitted minus what it absorbed. Okay? Okay, so then let's go to the next slide to try to solve our problem. So what is the problem? We have an athlete and she's sitting with no clothes in the locker room. And the walls in this locker room is very cold. The temperature is 15 degrees. Okay, so this is the temperature of her surrounding. So I'm going to write here, this is the T2. The T2 is 15 degrees. Okay, before I do anything, I'm going to already write this temperature in Kelvin. As we said, we use the temperature in Kelvin in our equation. So 15 degrees Celsius plus 273 will give us the temperature in Kelvin, which is 288 Kelvin. Very good, very important. Okay, we want to estimate the rate of heat loss by radiation, so this net flow, this delta Q over delta T, assuming that her skin temperature is 34 degrees. So she is radiating at this temperature of 34 degrees. That's the temperature of her skin, of her surface. And again, let me put this temperature in Kelvin. So 34 plus 273 give us 307 Kelvin. Okay, so this is very important. Don't forget to write the temperature in Kelvin. What else does the problem give us? The emissivity of her body. The emissivity of her body is approximately 0.7. Okay, we need that. They also give us the area of her body. The area of her body is approximately 1.5 meters square. The area that is not protected, okay, the area that is open in the air. With this, we can compute this delta Q over delta T, the heat that she's losing, the rate of the heat that she's losing by radiation. So we have to put all these numbers into this equation. The important step was to change the temperature to Kelvin. The rest is just putting numbers into that equation. We have everything. We have the emissivity. You put here 0.7. The constant we have, the Stefan Boltzmann constant, is this one. The area is 1.5. The two temperatures we have there, don't forget to raise each one to the power of 4. You put all that and you're going to get something very close to 120 watts. It's 119.3 more or less. Okay, so the answer of this problem is going to be something very close to 120 watts. Why watts? Because this is joule, unit of energy, divided by time, time in Celsius. So that's why we get watts. Okay, so that's the solution of this problem. There is an interesting comment here, which you as a student of biology know, which is if we are in a room that is too cold, our body will be radiating more than what it can produce and more than what it's absorbing from the surroundings. And there will be a point that we start feeling very cold, we'll start shivering now to try to increase this metabolic rate. But if this is still not enough, you may eventually die. So better to get protected. Okay, the last part of this slide is an interesting comment about thermography, now, which is a way to try another resource to try to detect if there is any problem with our body. Now, parts of the body that radiates more are usually a sign of a tumor or an infection. So if we get an image from the radiation from the body, we can maybe detect an infection. And parts that do not radiate much are usually signs of poor circulation. Okay, so this is the end of this slide, and and the end of this solution for this problem 1411 is the end of the discussion for convection.